Oh, hi there. Let's talk about related rates again. I really like this problem. Okay, so this is a cool problem, and there's a conserved quantity in here that one has to use in order to be able to do this problem correctly. I don't know. I think that you might really appreciate this. So, um, Farmer Alyssa, seen here on a tractor, her tractor, she's traveling at 3 meters per second on her tractor, and she's hooked up back of her tractor on a pulley to a bale of hay. So there's hay right here, and as the tractor moves forward, this right here is gonna go like meh, and then like the rope is gonna go like up like that. Okay. There's a pulley that's 6 meters off the ground, then we want to know. We want to know how fast is the bale rising when the distance from the tractor to the bale, horizontal distance, is 5 meters. This distance, this horizontal distance right here, is changing because the tractor is moving, right? So like dx dt is 3 meters per second, and we want to know how fast the bale is rising, and the height of the bale is h, and so we want to know dh dt. We were given this diagram with a problem. This part right here, this how fast right here, this part right here is asking what's dh dt, right? So that's our target quantity. We need dh dt. In order to get there, we're going to have to write down an equation that relates these rates of change. And we always start in these problems, it seems like, by relating the static quantities and then taking the time derivative using implicit differentiation to get the equation that relates the rates of change. Okay. Let's see here. So this traveling at 3 meters per second, that means that dx dt is 3 meters per second. So dx dt equals 3. And we want to know what dh dt is when x is equal to 5. So there's a conserved quantity right here in the length of the rope, right? So the amount of rope that Alyssa has as she's hooked up to this bale of hay is the same throughout the problem at all times, until the rope breaks, because like the bale of hay runs into the pulley, and then like who knows what happens after that. So this length of rope right here is fixed at all times. Let's call that L, right? L is constant. CST is constant. Okay, so there's a portion of the rope that suspends the bale of hay, and then the rest is in that part between the tractor. And so let's call that, say, lowercase l. Let's do lowercase l. So we happen to have that L is equal to L plus 6 minus H. Got parens around those, but I omitted them. And not only that, but then I've got this triangle relationship. I've got this triangular relationship between this 4.5 figure, x, and lowercase l. And so I know this, but I also know that 4.5 squared plus x squared is equal to lowercase l squared, because of this triangle right here. Even as the tractor moves, x is going to get longer, and the scripty l is going to get longer to make up for it. Okay. I really want this expression right here. I want this expression in x and capital, sorry, not capital L, capital L is a constant. I want that to be an expression in X and H because I need to answer a question about dH dt, and H doesn't appear in this expression. So how do I get H into this expression is through this thing right here. So this thing right here implies that I need to get L by itself, that lowercase l is equal to capital L minus 6 plus H. So let's take that and substitute it in for this thing right here. And then I'll have an equation in X and I'll have an equation in X and H. L is a constant. So let's write this out. Equals L minus 6 plus H quantity squared. So I've got something that relates my two state variables. Let's then differentiate with respect to time. Because X is a function of time and H is a function of time. So when I differentiate, 4.5 squared goes to 0. X squared is going to go to 2x times dx dt, because I've got a function inside of another function. I've got a composition of functions, so I chain out the derivative equals, let's see here. Let's do chain rule on this. So I'm going to have 2 times L minus 6 plus H times the derivative of the inside. L is a constant. 6 is a constant. H is totally not a constant. So times dH dt. So we'll start putting in stuff that we know and figure out how to identify the parts that we don't know. It says when the horizontal distance from the tractor to the bale is 5 meters, the horizontal distance from the tractor to the bale is 5 meters. That means x equals 5. So we're going to have 2 times 5 times dx dt is 3 equals 2 times, okay, I need capital L. And then this is my objective right here. dH dt is my objective. So I need to know what L and H are. And I feel like ooh. I know how to do it. Okay, I was looking around and I was like, I don't know L minus 6 plus H. I don't know L. I don't know how long the rope is. And I don't know what the height is either. But take a look at this. L minus 6 plus H. L minus 6 plus H is scripty L. That's this expression right here. And I happen to know that I have a triangle that has side length 5, that has side length 4.5, and side length L, which means I know what L is. Okay, so this part right here is L. Okay, so I know that L squared is equal to 5 squared plus 4.5 squared. Or that L is equal to the square root of 5 squared plus 4.5 squared. So then I get to put that right here. Square root of 5 squared plus 4.5 squared. Oh, and we are so close. We are so close. Okay. So let's cancel a 2, and then let's bring that to the other side. Done with my little scratch work here. So let's delete that. I really like scratch work. I think scratch work is really important. And I think drafts are really important too. So don't expect yourself to get these problems the first time you try them. Leave yourself room for improvement and do drafts. Sorry about the glass bottle. Okay, I want dH/dt. Periodically, I'm going to come back and be like, what am I doing? dH/dt. dH/dt. So let's solve. And lo and behold, I'm so super close. I know that dH/dt is equal to 15 over the square root of 5 squared plus 4.5 squared. Oh, and I'm done. And I'm done. It's a positive quantity. I think that's important to note. That thing right there is bigger than 0, and this is going up. H is increasing. Okay, so we got something of the correct SIGN sign. That was good. I'm having a hard time telling what the order of magnitude for this should be. This is something like this is going to be somewhere around like 6 or 7. So this is going to be somewhere around like something less than 3. Okay, that seems to make sense, because it probably shouldn't be any faster than the tractor is moving. It probably should be a little bit slower than the tractor is moving. Okay, let's review our steps, because I wasn't super explicit with this one as far as like what I was doing at the various times. Okay, given a word problem. In this case, we were given a picture as well. It's labeled, and we came up with an equation that related my variables, and I want that to be in the variables I'm really interested in, x and h, and it's not uncommon to start with something and then have to be like, oh, my equation was in radius, but actually I'm interested in diameter, or my equation was in circumference, but actually I was interested in one of the cross-sectional things. So there may be some like substitution to get into the variables that you're interested in, and I feel like the variables that you're going to be interested in are going to be strongly hinted to by the rates of change that are described in the problem statement. Namely, I have dx dt, and I'm interested in dH dt. So my variables that I'm really interested in here are x and h. And then I think the tricky part in this one was realizing that there was a conserved length here in the length of the rope. I don't know. There's a neat related rates problem. Hopefully that eliminates some of the various steps for you. Again, there's a huge variety in terms of problems of these, and the way to get good at them is to just like practice. And there are tons more videos on YouTube. So if you're not finding what you need from my videos, well, send me an email so I can make them better. But also check out other people's videos about related rates too. Thank you so much. I really appreciate your time today, and I'll catch you for the next video. Bye.